Okay, continuing on to problem 4. It says Tarzan, mass 85 kilograms, tries to cross a river by swinging from a vine. This vine is 10 meters long, and his speed at the bottom of the swing is, as he just clears the water, 8 meters per second. Oops, got a typo there. I got is twice. Tarzan doesn't know that the vine has a braking strength of 1,000 newtons. Does he make it safely across the river? Where in the swing would the vine have the greatest stress? So you say, okay, draw him a picture. Everybody likes drawing pictures. Okay, they make the problem a little clearer, and it's a good time. So here we go. I've got my vine. All right, I've got Tarzan. Now, let's see. Tarzan's going to be grabbing onto that vine, all right? Okay. All right, and let's see here. Okay, and he's going to be wearing his trademark loincloth here, right? Okay. All right. Should I make this like cheetah pattern on it? Anyway, whatever. Anyway, point is, let's see. Good enough, right? I wish I could do a Tarzan yodel. Never taught myself how to do that. Anyway, let's see. He needs some long hair. Well. All right, there we go. All right, so Tarzan is swinging on that vine. Right? Okay, and the point is he's going to go in this arc, right? Right? Okay, so here we go. So the point is, as he swings, we're trying to ask, when is that tension going to be the biggest? Because we're trying to see if the tension gets bigger than 1,000 newtons, the vine will snap. And so we want to know what's the biggest tension that vine gets. And so I'm going to kind of think about this and think about what's happening here and about the forces involved. So maybe I'll do a quick force diagram for Tarzan here. And if I do that, then I'm going to be like, okay, I really should have had that vine being tucked closer to his body. Oh well. There will be range forces. There will be a gravitational force, drunk, mg. And then contact, the only thing touching him is the vine. There's going to be this tension going this way. Now, I want to think about this in terms of coordinate axes. So I'm going to think about radial and tangential. Okay, that's the way we analyze it. His motion right now, if you had to draw a velocity vector in, it would be this way, wouldn't it? All right, tangential. We always draw our first axis tangential. So T is going along the perpendicular to the motion axis, which is the radial direction. So it's just mg that's got to get split up. Right? Okay, into radial and tangential. I don't know, I didn't dot properly. Anyway, and so you say, hey, let's call, that doesn't matter. Point is, hey, this part of the force, that part is tangential along the direction of motion. This is going to be making him get faster, isn't it? It's pushing with the motion. So he's going to get faster as he goes. And so you say, when I get to up and down, I'm not going to draw Tarzan all over again. I'm just going to say, look, hey, it's Tarzan. There we go. And that vine is up and down, right? Right? You say, well, at this point, there'd be a gravitational force, which is the same size as there. And there's going to be a tension going that way. There is no force tangential now. There's nothing speeding him faster or slower. After this, isn't there going to be a gravitational component going against the motion? So he's going to be getting slower as he goes up. You say this is when he's going to be the fastest. He'll be done accelerating when he gets to here. I know this was a lot belaboring a point that we already know, because from energy last year, we of course would say, hey, we know that as he goes down, he's losing gravitational potential, gaining kinetic. And as he goes uphill, he's going to be gaining potential, be losing kinetic. And so you say, this is when the kinetic is largest at the bottom of the curve. And so you say, okay, so that's the point we want to analyze. That's when he's going to be going the fastest. Why does that matter for tension? Because we know that we're going to look at the sum of the forces in the radial axis is mass times acceleration centripetal. And that centripetal acceleration, that's going to be v squared over r. When he's going, the radius is constant, the m is constant. The total force in the radial axis has to be the biggest when the v is the biggest, when he's going the fastest. Do you see that? And so when I do this here, at this point, my radial direction is going to be, how do I write the forces? Well, is it going to be T minus mg or mg minus T? Well, we always call toward the center of the circle positive. So it's going to be T minus mg. If he was over here, right, this angle would be theta, say, and this would be T, mg cosine theta, and this would be mg sine theta. And you'd say, hey, mg cosine theta and T, it'd be T minus mg cosine theta, right? You see, now cosine, it's the biggest. When is cosine theta the biggest? When theta is 0. Aha, which is what will happen here. That angle will crush down, right? That angle here is that angle here, right? That's going to squeeze to 0 when you're here. That's when the cosine function will be the biggest. Mg is not changing as it goes, so it's just cosine theta. You say, once again, you say, this force that tension has to fight against to provide that inward force it's the biggest here. That component parallel is biggest there. So again, the bottom is where we want to look at. Oh my gosh, that was a lot proving something that's pretty straightforward, but that's okay. So this is the point where T has got to be the biggest. Okay, it's at the bottom when he's going the fastest, right? And that tension has to fight against all of gravity. So that tension will be the biggest when he's at the bottom here. So looking at this, then you say, okay, that T, moving over here. T is mg, move the mg over. It's going to be mv squared over r plus mg. Hey, I know all these values, right? I know his mass is 85. I know the speed at the bottom, they told me, was 8 meters per second. The radius, we know the vine is 10 meters long. And then 85 times 9.8. Because remember, G is a positive 9.8, okay? And you say, so if I punch in my values, I will get 1,377 newtons about. And you say, hey, that tension, that's that maximum tension we're getting at the bottom there. You say, you know what? That's greater than 1,000 newtons, which is the breaking strength of that vine. So, snap. Okay, Tarzan is going for a swim. All right, and that is problem 4.